Okay, so we're going to start with Kepler's laws of planetary motion. He has three, just like Newton did, but he came before Newton's time. Okay, so he discovered these laws and wrote these laws before Newton was around. Kepler's laws of planetary motion give us good, pretty detailed descriptions of how the planets move, what their orbit looks like, the time it would take them to orbit, all that kind of stuff. Okay, he gives us a pretty good description of the motion of these planets with reference to the sun. Okay, so Kepler's first law says the path of each planet around the sun is an elliptical path. Okay, it's not a circle, it's an elliptical. Okay, and it has the sun at what we call a focus point. So in this image I'm going to show you, you'll be able to see that the sun is at one of these two focus points at any point during this elliptical path. All right, so here's this planet. It's orbiting in an elliptical path, not a circular path, and the sun is at a focus point. Okay, there's two kind of focus points here. The sun will be at either one of those at any point during its orbit. Okay, so his second law tells us that as each planet moves through its orbit, it's going to cover the same amount of area or equal amounts of area over equal amounts of time. Okay, so this is any planet that's orbiting the sun will have will follow these rules. Okay, so as a planet moves in its orbit, it covers a certain amount of time here. As it covers that certain amount of time, this area, this triangle of area, will be equal to this triangle of area, which will be equal to this triangle of area. So as you go around this orbit, it'll cover a certain amount of time. If you can draw little imaginary lines to the sun and build that triangle, for every interval of time, you should get the same amount of area as to an equal interval of time on another part of the path, another section of the orbit. The third law is do you need to go back? Okay. First two laws give us conceptual ideas about what we need for these planetary motion. The third law gives us an equation that can help us solve for the radius and the period of a planet. Okay. So this is Kepler's third law. Okay. It's explained in words at the top and then given in equation form underneath. Okay. So the word form of it says the ratio of the squares of the period of any two planets that revolve around the sun will equal the ratio of the cubed, okay, or the cubes of their mean distance from the sun. Okay, so I know that's a lot of words in a little bit of space, but T is the period for any two planets, and R is their distance from the sun. Okay, so R of the radius of planet A over the radius of planet B, if you take that all cubed, that will equal the period of planet A over period of planet B, and if you take that squared. Okay. What does the period tell us?
Amount of time.
The time it takes to get around one revolution. Okay. So remember, time is a big T, so that's period. It's the time it takes to make one complete revolution. What would the period then be of the Earth?
365.
365 days. Okay, so if we're looking at the period of the Earth around the sun, be 365 days. The Earth rotates itself one full time in one day. Okay. So this top equation here is putting all of the period on one side and all of the radius on the other side. All of this bottom equation is rewriting to make all of planet A on one side and all of planet B on the other side. So all we did is rearrange this equation right here to make this bottom one. So it would be the radius of planet A cubed over the period of planet A squared would equal the radius of planet B cubed over the period of planet B squared. Okay. I think it's a little easier to do it this way, putting all of one planet on all of one side. You can do it either way. It makes absolutely no difference. The reason that it's rearranged is so that you can see this ratio, okay? This r cubed over t squared will be the same for every single planet that we're looking at that orbits the sun. Okay, this radius cubed over period squared will equal the same value for every planet that we look at. Okay. Okay, so we're looking at 2 planets, Mars, and we're using Earth as our reference, and the sun is one of our focus points. Okay, so that's what we're looking at in reference to the sun. So Mars has a period where the time it takes for one revolution equals 1.88 years. Okay, so that will be the T of Mars. We want to determine the distance from Mars to the sun using Earth as a reference. So that will be R sub ms will be what we're solving for here. Distance from Mars to the sun. So the distance will be its radius. I've given you a value here of distance from Earth to the sun. That will be our R sub es. And then what would be the period of the Earth? Yeah, 1 year. Good. So if we know that T of Mars equals 1.88, we know the radius from the Earth to the sun is 1.50 times 10 to the 11th. And we also know that period of the Earth is equal to 1 year. So we want to solve for the radius from Mars to the sun, okay, or the distance. Okay, so we're going to solve for R sub ms, and that's going to be cubed, because outside the entire parentheses is cubed. And then we're going to put that over the distance from the Earth to the sun, which is 1.5 times 10 to the 11th. And that whole term needs to be cubed. All of that will equal the period of Mars, which is 1.88, and that needs to be squared. All over the period of the Earth, which is 1, which also needs to be squared. So mathematically, to solve this, my steps would be to cube this unit first, or this term first. Then we'll multiply it to get it on this side. Okay? So I'm going to go ahead and solve this whole right side of the equation first. 1.88 squared is what?
3.375 times 10 to the 33rd.
Okay.
What did you ask for?
Just the 1.88 squared.
Oh, no.
2.53.
That was the 1.5s.
Okay.
3.5.
Tell me. Okay. So the whole right side of the equation should be the 1.88 squared divided by 1, which is 3.55. Is that what you told me?
3.53.
3.5.
Whatever. Yeah.
I can't get anything right. Okay. So that's going to equal radius ms cubed over, and what's this cubed? 1.5 times 10 to the 11th cubed. Tell me what the value for that is.
3.8
To the 33rd. Okay? So now we need to multiply by this term right here on both sides. So we need to take 3.53 times this number to get r sub ms cubed by itself.
I got 1.833.
1 times 10 to the... Are you sure you multiplied?
Yeah, I just put 3.53 times 3.38. Oh! Whoa, wait, I messed up.
Okay, so we multiplied that across. That's going to equal the cube of RMS. So we need to take the cubed root of both sides. Do you know on your calculator how to take the cubed root? Okay, if you hit math, and then scroll down to number 4 where it says 3 and the little square root button, hit enter. Then you can go second answer, and hit enter again. Okay, these are a little bit more useful. Okay, we use these more than we do Kepler's laws. So Newton wondered how the moon stayed in its orbit. Okay, if we had the planetary motion part figured out, we didn't know about the moon. Okay, so he started studying this moon concept and why it stayed into its orbit. Okay, so we looked at the gravitational force of the Earth and of the moon, and between the two, and how gravity was exerted on the surface of the moon, what it would be like. Okay, so here's Newton's law of gravitation, universal law of gravitation. This is what you need to have in your notes right here. These two, not as much. This one you do have to have.
Which law is this?
This is Newton's universal law of gravitation. Okay, so that needs to be in your notes. Okay. Any two objects will have some sort of gravitational pull toward one another. Okay, depending on their mass and depending on how far apart they are. Okay, so where does the source of our gravitational pull come from? Yeah, the center of the Earth. The Earth's mass is infinitely larger than ours. Okay, so we are all attracted to the Earth and to the center of the Earth. Okay, that's what keeps us down. That's what keeps us on the surface of the Earth, is that we are attracted to the Earth because its mass is so large. However, even small objects on the Earth have gravitational pull towards each other. It will not be big enough for you to feel. It won't be big enough to start out of nowhere pulling you towards one another. Grace and I, even though we're this far apart, have a small gravitational pull, but you don't see us starting to float towards each other. Okay? That doesn't happen. Okay? But we do exert some sort of gravitational force on each other, just like I exert a gravitational force on this table or on this water bottle, whatever. Okay? So here's the equation that he came up with to solve for gravitational force. Okay, he compared radius, he compared distance from the Earth, he compared things on the moon, but we've got to take into account both masses of both objects. Okay, one of those masses might be the Earth's mass. It might be two small objects. We're trying to find the force between the two. You can do lots of different things with this equation. So this force that we're solving for here is force due to gravity. So you can put a little g in there if you want. These paragraphs aren't super important for your notes, but you do need to get in this equation.
So wait, did you say we don't do that?
The paragraphs, no, not so much. Just kind of talk about how we get there. Okay, that's a force due to gravity. You don't have to put the little sub g, but you can. It is a gravitational force. Here's what the components of this equation stand for and what they mean. F is our gravitational force. G is what we call the universal gravitational constant, which is 6.67 times 10 to the negative 11. That's a constant, which means that's what its number will always be. G will always be 6.67 times 10 to the negative 11th. It's got a lot of these units here. These units are what we need anytime we're solving one of these equations. Our distance or our radius has to be in meters. Our masses have to be in kilograms. Okay?
Oh my.
Then the M1 and M2 are just the mass of each of those objects. So let's go ahead and try a problem here. This tells us one mass is 50 kilogram, one mass is 75 kilogram. What is this 50 centimeters telling us?
The radius.
Radius. Okay. So we want to find the gravitational force that they exert on one another. Do you think that there will be a difference in gravitational force depending on the person?
Yes. Yes.
Like, do you think if I'm one of the objects and Grace is one of the objects, will I exert more of a gravitational force or less of a gravitational force? Or will they be the same?
Depend on the mass. Right?
Nope. It'll be the same. She and I will both...
Then obviously she ought to have more.
Obviously...
Basically, I'm
Okay, we're going to plug in our gravitational constant. Our mass is 50, and our mass is 75. Yep, we're going to use the radius underneath. So our r needs to be squared. Is our r in the correct units? Is the radius in the correct units?
No, it's supposed to be meters.
Needs to be in meters, so that means we need to move the decimal place 2 places to the left. So it's 0.5,
Oh, I see that.
and that needs to be squared. Okay, so our force, gravitational force, or our just F here,
Is on the edge.
1 times 10 to the negative 6. What's our units for force?
I got.
Meters per second.
For force?
I was good. Meters squared.
Newtons.
Newtons.
What the? What are you laying with?
Okay, the units that go with G kind of cancel out all of our other units to make it a Newton. Okay?
What'd you get?
1.6 times, or 1 times 10 to the negative 6.
Yeah, that's right.
All right.
Yeah.
Okay, let's try another one. This one's a little tricky, but we're going to walk through it. Okay, so it says force of gravity between two masses was 14 newtons when they were 10 meters apart. So these two objects are 10 meters apart. The F sub g between them is 14 newtons. The distance between them changed, and the force became 56 newtons. How far apart were they then? Okay.
I'm gonna have to write this.
So if their force was 14 newtons when they were 10 meters apart, and if the force became greater, do you think they got farther apart or closer together? Closer together. We're going to find out exactly how close they got. So we'll use our equation, F equals G, M1, M2 over R squared. Okay? In our equation, we were given force and radius for this first part of our question here. Okay, 14 newtons as our force. We know that our G is always 6.67 times 10. You really have to put it in there. It's going to mess your problem up if you don't have it in there.
That's line about it.
Okay, we don't know M1 or M2, so we're going to just leave them there. What?
They were 10 apart.
Oh, this is different.
Oh yeah, this is a different one. Okay, so now they're 10 meters apart, so that means our 10 needs to go down here and it gets squared.
That's 100.
Yep.
Oh, wow. Wow, you're really good.
Kira was literally.
To solve for this whole M1, M2 term as a whole. Because from situation 1 to situation 2, when these two get closer together, does their mass change at all? No. Okay, so the mass doesn't change, which means for the second part of our problem, we can use that same M1 times M2 term as a whole. Okay, so we're going to solve for this right here, M1, M2 as a whole, and then we'll move on to the second part. So if we want to solve for this, my first step would be to divide by the 6.67 times 10 to the negative 11th. Do that on both sides.
Oh, clear.
2.1 times 10 to the negative 11.
To the positive 11th. Should be positive 11th.
Mine came out like
Did you plug in negative 11 for the 6.67?
not equal to equal.
I got positive one.
The calculator's messed up. See? I typed it in.
I need to take my 100 and multiply it on both sides.
Divided by.
So I'm going to take my 2.1 times 10 to the 11th,
Just gonna make it.
and I'm going to multiply it by 100, which makes it,
Y 2.1 times 10 is 13.
Okay, so the reason I took it multiplied by 100 was because I wanted to get M1, M2 by itself. So I'd take it by 100 on this side, if I need to take it by 100 on this side also. Okay. So that means my mass of these two objects put together is 2.1 times 10 to the 13th. Okay.
And then half and half, they're exactly the same height.
It doesn't make a difference. What if one of them takes up 3/4 of that mass and the other one takes up the other, it doesn't make a difference because between these two scenarios, the mass of those both objects don't change. Okay, so those two multiplied together would be the same for both.
So what were we looking for?
Now we're going to look for how far apart they were in the second scenario. Okay, because for the second part, we only have a force. We don't have either the masses or the radius, but now we have a mass and we have G. Okay, got it? All right, I'm going to give myself some room here. So now we're going to plug into our equation and solve for radius. So now our force is 56 newtons. We know our G. So same here, I'm going to start by dividing by the 6.67 times 10 to the negative 11th. I'll do that on both sides. So if I take 56 divided by 6.67 times 10 to the negative 11th, I get 8.39 times 10 to the 11th, and that's going to equal my masses over r squared. Okay, how do we make this r squared by itself? Divide what?
2.1.
2.1, do what to it?
Divide it over to the other side.
Well done.
And remember we switched the places.
Oh, we have to-
8.39 from 2.
We have to put the R over there and the...
We switched their places. Okay, if our variable that we're solving for is on the bottom, we can just switch those two places. So we need to take 2.13 divided by 8.39 times 10 to the 11th. We'll switch those two places. 2.1 times 10 to the 13th divided by 8.9 times 10 to the 11th gives us an r squared value of what?
I got 27.4.
I got 25.
I know, me too.
Okay, so our r squared value equals 25. We take square root of both sides. Radius equals 5 meters. We're trying to solve for F. Okay, we know G. Here's our mass of the Earth and radius of the Earth. Those two values are ones we'll use a lot in this chapter, so you might want to write those down somewhere that you'll be able to see, either on your equation sheet or somewhere easy to access in your notes. That will be a value that I give to you on tests. Okay, you'll be given the radius of the Earth and the mass of the Earth because they'll use them a lot. Okay. So what do you think this means here that it says it's orbiting 2 Earth radii from the center?
It goes around twice.
Here's the distance of our radius, okay, from the center of the Earth to the surface. So all it's saying is that there's another length here that's equal to r that it's orbiting at.
Wait, can you go all the way around with that?
Like this?
Yeah, that's better than me, that's not
Okay, so now our radius is just going to be 2r. Okay, so we'll take 2 times the radius of the Earth and we'll square that whole entire thing in our problem. Does that make sense?
Yeah.
Okay.
Wait, but we already have 2 R. We already have radius squared.
Now we have to take 2 times the radius and then we square that whole thing. Okay, that's all right. So we're going to take G, which we know is 6.67 times 10 to the negative 11th. We're going to take the mass of the Earth as one of our masses and the mass of the satellite or the spacecraft as our other mass.
Oh, no.
Okay, this here where it says we must convert to meters, I already did that for you, so you don't have to do that. Okay, so there's our M1 times our M2. Okay, we're going to divide that by our radius, which we already said was 2 times the radius of the Earth. So we're going to take 2 times 6.38 times 10 to the 6th. And then we will square that whole entire term.
Wait, which one did we have to convert?
Well, I already converted this one to meters for you. It was in kilometers originally, but I went ahead and converted it. So you don't need that.
For the bottom, I got.
Okay, just wait 1 second.
Wait, so you get, where do
Okay, so when you take 2 times the radius of the Earth, we square that entire thing. Take the masses, divided by that, we'll take it times our gravitational constant.
It's to go see Mr. Euler.
You don't need all these equations here. We're going to solve, I'm going to show you how we get to this final equation, which is little g equals big G times mass of the Earth over r squared. This equation you use to solve for the acceleration due to gravity, okay, which on the Earth's surface is 9.8. So if I use this equation right now, and if I solve for the acceleration due to gravity on the Earth's surface, okay, which I'm going to show you that we can do, I'm going to take g equals 6.67 times 10 to the negative 11th, multiply that by this whole term of the mass of the Earth over the radius of the Earth squared. So that's 5.98 times 10 to the 24th over 6.38 times 10 to the 6th, and that's all squared. Okay, if I do that, what should my acceleration due to gravity be? Because this is on the Earth's surface. What should I get? 9.8 meters per second squared. So if you plug these numbers into your calculator, you should get 9.8 meters per second squared because that's the acceleration due to gravity on the surface of the Earth. Okay, so the derivation of this equation starts with the law of gravitation that we know right here, this force due to gravity. All we did for the second part is we substituted in the mass of the Earth for m sub 1. Okay, so one of the masses, if we're looking at acceleration due to gravity, has to be the mass of the Earth, since that's the biggest mass that we do look at, and that's where our source of gravity comes from. After that, I substituted in m times g for our force due to gravity. Okay, our gravitational force is mass times gravity, so all I did was take the object's mass times the acceleration due to gravity and plugged it in there. And then for the last step, all I did was cancel m sub 2 on each side. So I got rid of m sub 2. That leaves me with acceleration due to gravity equals gravitational constant times me over r squared. So this is an equation that you will use a lot, and you'll use it to find the acceleration due to gravity. Okay? Try this one on your own.
You hate school?
I didn't get that, friend.
What? Did you blow away from your brain?
Hey, Grace. I can feel the gravitation.
Here's half elephant.
Can I write that on a ballot? I got
Yes.
card. I should buy one just for that. Just to
What'd you
see.
get? I got that.
I would love that.
I would actually, honestly, if I
I didn't
didn't
get
get
that
that,
one.
I would
You get
just
9.7.
write a whole
Is that
list
four?
of puns.
Yes.
What?
A whole list of puns.
Oh my gosh, that'd be awesome. I love puns.
Puns are the best.
Now we're answering to that.
I should write a musical called Pun. Play on words.